is more or less the last section in this series of presentations. Combines some of the concept that we've looked at before. I mentioned the need to predict reliability and thereby predict safety of components which have to operate in loads for long periods of time. We talked a lot about the fact that cracks can grow slowly with time in moist environments, which invariably occur in almost every condition which we want to use them. So what I'm going to talk about in this section is how we combine our knowledge of statistics of failure, our test procedures, and so forth to predict the lifetime of a part under stress, and toward the end of the section give you an example of how we actually did this for one particular component. So first of all, just as a reminder, I showed that cracks can grow slowly with time, which means that our measured strength decreases with time. This is important. So I can't always design with the highest strength. I have to know what will happen after long periods of time. So the fact is we can combine strength analysis with fracture mechanics to account for delayed failure. And what I'm going to show you, and the analysis and the models are fairly new. Not clear that everyone will agree with the exact model that we use, but I like the use of this phrase that all models are wrong, but some models are useful. So we have created a model which we will use to predict failure, and I'm sure over the years new and better models will be developed. But this one works to give us at least an answer under conditions where we would know nothing about what the safety of a particular component would be after a long time in service. So let's go back to the fact that cracks grow with time. I showed earlier in section 2 that we used a log function to describe the crack velocity as a function of stress intensity factor, but that really doesn't work very well for various reasons in the engineering analysis of crack growth. So instead of using that logarithmic function, we chose to use a power law. The stress intensity factor, the critical stress intensity factor here is really just a number that uses to avoid the dimensions in the equation. So this is really an expression of crack velocity as a function of stress intensity factor with an exponent n. And the value of n is a measure of the extent to which subcritical or environmentally enhanced crack growth occurs in this material. So this then, if we were to look at a fracture mechanics specimen, say one in a double torsion specimen or a double cantilever beam specimen, this expression would be used. But because we are looking at real flaws and we want to simulate actual flaws, most failure initiating flaws occur during machining or finishing. I've said that numbers of times. And because you're introduced, machining is an impact process, impact-like process, they are accompanied by a stress field. I strike the material in some way, and not only do I produce a small crack, I produce some damage and some stress near the crack. We talked a bit about that too. And all of that stress and the flaw itself can be simulated using a Vickers hardness indenter. And by doing this, we can modify, this causes a modification in that exponent in the expression I just showed. It doesn't change the equation at all, but instead of the value of n, which we would get from fracture mechanics tests, we use an n prime, which is directly related to n mathematically. This just means that I think we have a more realistic value for this exponent, which we will use in our calculations that we would have if we didn't make this assumption. The other big effect and the expression for time to failure is that it's dependent solely on measurements of fracture strength. There are numbers of expressions of crack growth with time that invoke the use of stress intensity factor, but they also include the need to measure flaw sizes. That's very difficult. As it turns out, in a paper by Ed Fuller, etc., written a number of years ago, and I'll come back to this later in my example, an expression was derived for time to failure which was solely dependent on values of these material parameters or experimentally derived parameters which are only strength dependent. So this is the equation of relevance, and I'll show you in a moment how we obtain all of these values. S is what I call the initial strength of the component, that is, or of the specimen that I'm going to test. That is, before anything has happened to it, I make the specimen and I test it. S sub v is the strength of an indented reference set of specimens, and I need that because I've decided that I'm going to use indented specimens to do my test because I want to measure the effect of n prime rather than n. So it requires that I make an additional set of strength measurements. Sigma is the tensile stress in the component. I obtain that typically by finite element analysis. And lambda and n prime are crack growth constants, which are obtained by a process known as dynamic fatigue, and I'll show you what that means in just a moment. But basically it's measuring the strength of the material as a function of the rate of loading. The slope of that is then n prime, and a lambda is an intercept on that particular curve. So it's another way of getting crack growth data, and known by the term dynamic fatigue. So then I want to go through briefly and talk a little more about how we obtain those parameters. So typically one would like to do biaxial testing at rapid loading rate in an inert environment to get that baseline strength, that original strength. So it assumes surface flaws. Instead of doing biaxial testing, you might have to do other kinds of testing, but typically biaxial testing will give you the best kind of data. As I just mentioned, n prime and lambda are obtained from, again, biaxial strength on indented specimens in water because we want to get the worst conditions as a function of loading rate, and I'll show you what a curve looks like in a moment, the term being a dynamic fatigue. Maybe not the best terminology, but that's historically what it's been called. The strength of the indented specimens, S sub v, is obtained in exactly the same way as I did the baseline strength. I do it on indented specimens instead of as finished specimens, but in an inert environment at rapid loading rates. And then the stress in the component, typically I would do by a finite element analysis. Sometimes I think I know what that number might be, but one would like to do some quantitative values. So you could pick a different stress in the component if you know that in a different way. Let me show you something about dynamic fatigue then. And again, there is an ASTM standard that tells us how to go about doing this. It's a standard method for determination of slow crack growth parameters by constant stress rate strength testing at ambient temperature. And there's a lot of detail on exactly how you do this. There's some certain caveats when you do it. The stressing rate range must be a minimum of 3 orders of magnitude if you're going to get accuracy or good enough accuracy to do the test correctly. And use, at least we feel that use of indented rather than finished specimens simulates the worst possible conditions, and then you must establish the strength of the indented specimens. And so a dynamic fatigue curve for glass discs, I'll come back to this later when I show you the example again. So here's what I get. I get a measure of fracture stress as a function of stressing rate, and you can see here over many orders of magnitude, and I can calculate that from that the exponent n prime, and I can calculate this value of lambda. So this kind of data gives me the kind of data, at least 2 of the parameters I need. I told you how to get the other parameters as well. And so we saw that the S sub v I have to get by an inert environment and rapid loading rate, and the stress in the component by finite element analysis. But in strength testing, you want to, just some hints, uniaxial tests are the most frequently used. If you're going to do that, use 4-point, not 3-point bending. And again, the edges of the specimen are most likely to contain severe flaws, so you need a rounder chamfer. So unless the component has edges under strain and I need to know what might happen to the edges, the biaxial tests are better. But there's another complication, and that is there can be uncertainties in each of the measurements here. And there are ways to determine through coefficient of variation calculations that you see here in which I can take into account the combined effects of uncertainties. It's a little too complicated for use in this explanation, but the uncertainties in each of these measurements can be combined in an equation that looks like this. so that the standard deviation of the end result that I measure, namely the time to failure, is a function of the variation in this manner of each of these variations in each of these components that are directly measured. And this coefficient of variation technique works as long as the uncertainties in each of these portions of the equation are not greater than about 10%. And so this technique would work very well. So the variation here is simply the standard deviation squared. So what I do is, going back just a moment, I take all of these data that I showed you, just running backwards a bit. All of this data that I took goes into the equation. So I measure each of these parameters, the crack growth parameters, the tensile stress. I know in some way, maybe that has zero uncertainty, maybe not, but the strength of the indented specimens. All of these are statistics in nature, and I showed earlier how you determine some of the uncertainty in strength measurements. You will use those in determining the uncertainty in this time to failure. Moving forward then, what I want to jump into is how we use this to actually determine in a real material. A number of years ago, we were approached by the Federal Aviation Administration, who want us to assure that an aircraft window in an aircraft would not fail in flight. And this was an unusual aircraft window in that it was all glass. It was a BK7 borosilicate glass, and they needed to be sure that the requirement was there was a 90% survival probability, and the confidence in that survival probability would be plus or minus 2.5%, 95% confidence. This kind of is a picture of what that aircraft looked like. So we actually went through this procedure in order to calculate for them what the likelihood of the time to failure was. In other words, how long would such a window survive under the conditions in which they gave us. So the glass windows were as polished. They had to be optically transparent, BK7 glass. They were protected from damage, but they were under stress. So that we were not going to see further damage after the windows were manufactured. Again, this is the equation. These are all the parameters I showed earlier. How did we go about obtaining these 5 parameters? So for us, we did biaxial flexural testing on by ring-on-ring tests in an inert environment. There were 31 glass discs. They were finished identically to the components that were used, and fractography was used to identify the fact that the failure sources were similar in all the failures. We measured the biaxial strength of the indented specimens in water as a function of loading rate to get dynamic fatigue, the dynamic fatigue data, and I showed you that data a little earlier. We measured the strength of indented specimens and by a rapid loading rate in an inert environment. In this case, we used 33 discs. And the final analysis carried out by the window manufacturer gave us the stress in the component. So in principle, we had all of the data we needed, and this is all the data you see here. One of the points I would make here is that even before a more recent analysis, it was pretty clear. I talked about the difference between 2-parameter Weibull and 3-parameter Weibull, that the 3-parameter Weibull function fit the data a whole lot better than 2-parameter Weibull, and this is the expression we used to determine the statistical distribution of the failure times that we're interested in. And just to illustrate why 3 parameters almost always better than 2-parameter Weibull. So here are the values of the parameters for each of the measured material constants that you saw. The strength was roughly 110 megapascals, standard deviation of 3 point something. N prime I showed in the earlier graph with a standard deviation. The gamma, which is part of the dynamic fatigue data, that's a 10 to the 27th power. These are all very large numbers, but that's just a function of how the test is carried out. Here's the strength of the indented specimens, a slightly smaller value than the machine specimens, also with a standard deviation. And from that, we also should point out that the window stress is determined by the manufacturer with something like at 8.63 megapascals. And we went through the finite element analysis that you see here, or the coefficient of variation analysis rather that you see here, and calculated what the time to failure was given the uncertainties in the error propagation procedure. And so we calculated from that the time to failure was something of the order of 2.83 times 10 to the 12 seconds, or 78, 10 to the 8 hours. That's a very long time. But what I didn't say is that this only pertained to the specimens that we measured. What do actual windows look like? And so this is where the scale up, the tolerance limit, and scale up procedures become important, because this would tell us, yes, you're perfectly safe. This is a very large number of hours. And as it turns out, if you go through the scale up, that's for the 76 millimeter diameter specimens. If you go to the window sizes using these concepts of tolerance limit and coverage, you get to the following values. And it turns out that, depending on what coverage you want, so in other words, now here we are, here's the 90% coverage, so this would be somewhat equivalent to the 90% safety level that the FAA required. The set of windows, even though they're much larger than the set of specimens, we could expect that the time would be reduced by only about 50%, 0.41. But you can see as your degree of safety, the amount of coverage and your guarantee of safety over the extent of the total number of windows or the total area of the windows increases, now I start to significantly reduce the possibility of the time to failure. Now it's only 7/100ths the time to failure here. Still large enough to satisfy the FAA's requirements, but it's clear that as I increase my degree of assuredness and guarantees on the safety of my part, I'm going to reduce the possibility of time to failure, or increase the probability of time to failure. That's important. But as you go from specimens to components, again, you expect that you're going to see a difference in the numbers that you achieve. And so this analysis can be applied to any material. I showed you the kind of data you need. Some easier or harder to obtain, but the procedure is very straightforward. The uncertainties in all of this data is required, but again, one knows that. And I think it's a pretty straightforward way of gaining some confidence that you're preparing a safe and reliable component that will last as long as you need it to last. And the engineer who's developing the material gets to decide, based on the size and stress level in the component, how safe you want to be. So summarizing, I think for this part, that the advantage of this kind of modeling is that all the data necessary for failure probability can be obtained from fracture strength measurements. Very straightforward. Same kind of measurements you would normally do for any ceramic material. You obtain the data under the most severe conditions expected in service, and you use a propagation of errors approach to combine uncertainties in the data. That is important because the uncertainty, it's the uncertainty of the data that you really need to know. And that the scale up, again, makes use of these concepts of tolerance limit and coverage to give you what the real uncertainty in the actual components is going to look like. And then finally, I tried to say two-parameter Weibull functions are probably not the best fit to experimental data for any application. In fact, the argument I would make is let the data decide what the distribution used is the best fit. What distribution should you be using? But three-parameter Weibull works quite well in most cases. That modern statistical models and computer technology allow us to determine best fits of numbers of distributions that we want to look at. One thing I didn't say earlier, but that you have to look at the strength distribution and make sure that they're not bimodal, that is, that they're not failures from sources other than what I should expect in service, and any outliers you have to account for, and again, it comes back to the need for fractographic analysis is needed. And another point, I talked about finite element analysis as being a rigid number, but there can be uncertainties in the finite element analysis as well that you have to be cautious about. Any uncertainty in this will lead to further uncertainty in my predictions of time to failure. And then finally, this kind of statistical methodology is applicable to a wide variety of materials. In fact, it's more than just ceramics. You only need some functional relationship between failure, Doesn't have to be fracture. It could be electrical failure, something of this sort, and measurable parameters. So the statistical application, the expression itself is for the fracture of brittle materials for crack growth, but the fact is the approach to failure of any kind, can be somewhat the same. And again, I give you some key references into other things to be looking at that fall into this category. I think I have one more on here, and again, let me know if there's questions you have on some of this. In this final section, what I call a summary, I just want to reiterate some of the important points that I tried to make over the course of these lectures, stressing some of the critical ideas, I think, and maybe something of what's new of what I'm trying to say about how one understands, predicts failure, reliability, and so forth, which I think is still a continually important field, and the techniques of being able to do this accurately are gaining in stature, I think, with time. So I will just run through briefly some of the significant points, some of which I said before, but I'll say them again. And the fracture mechanics, the ability to apply fracture mechanics in brittle materials has been the key to understand the failure of these ceramic materials or any other material that behaves in a brittle manner. And secondly, this point that fracture toughness is a test-dependent parameter, rarely used directly in choosing a material. I stressed in predicting reliability, time-dependent failure, we went out of our way to avoid using stress intensity factors. It's much easier to do strength testing, a better way to go about it. And I showed you a lot of fracture mechanics tests, so you can see that one may not give answers to another. I keep saying there's standardized methods available to determine fracture mechanics parameters as well as strength. And if one is going to conduct these tests and have faith in the numbers that you obtain, strongly suggest that you go look at the standard and as best you can follow the dictates of the standard itself. I tried to show that we're developing, and we're in the midst of developing, new statistical procedures. They've been out there in the statistical language for a long time. What we've tried to do with my colleagues at NIST is to transform them and make them accessible to the engineers in the field. Statisticians are aware of a lot of these procedures, but they're not easily used, nor do people who are doing engineering work in ceramics or any other material likely to be familiar with the techniques that are available. So when I say the words tolerance, limit, and coverage, those terms have been around for a long time. They just are not ones that we in the materials communities are using to establish minimum strength of materials of components. I think I pointed out microstructure plays an important role in fracture toughness and strength. So the same material will not behave identically to another piece if you heat treated it differently. In other words, the chemistry could be the same. If the microstructure changes, the fracture behavior will change as well. And so obviously you need to go see what the microstructure looks like. And that gets back again to this idea, you can't do too much fractographic analysis to understand why fracture occurred and at what strength. I tried to present to you a method for predicting time-dependent failure of components along with the ability to determine the confidence in these predictions. In other words, I can predict failure probability. There are publications out there that say the time to failure for this material under this stress will be such and such. What we've tried to do here is tell you how good a prediction that is likely to be. In other words, what is the uncertainty value that I should assign to that prediction? And that's particularly important. Do I know that within 5% or only within 100%? I hope I've tried to show that earlier on, that these two techniques are very useful. And I want to end, but so sort of leave in your mind that we don't know everything, particularly about the mechanisms of what's really going on and what we need to put some time and research into. I have said a number of times we have little data on environmentally enhanced crack growth in most materials of interest. So of the thousands of materials available in the world or whether we might want to make tomorrow, there's no way of predicting their stress corrosion, their delayed failure behavior, their crack growth behavior. We are forced to go measure it. We don't even have a method by which to approach that problem. We don't know the primary factors governing the slope and position of crack velocity stress intensity curves. We don't know the actual stress at a crack tip. We presume to know it from the elastic properties of the material, but it may not. And we use fracture mechanics, and I've encouraged you to use it, but it really may not give the right picture of what's going on at an actual crack tip, and difference in behavior may be due to different crack tip structures. These are kind of controversial topics. Again, what mathematical expression should I use to fit our crack growth data? I showed you two different ones, one being an exponential chemical rate theory, which appears to be more fundamental, but the stress dependence in that expression is somewhat arbitrary. And whether my empirical crack growth law is sufficiently robust to use to predict failure times is still open to question, but it's available to us, and I think it's a better solution than anything else we have at the present. We have almost no knowledge of temperature dependence of crack growth in ceramic materials, nor we have good interpretation of what data exists out there already. So when you start talking about elevated temperature behavior, there's very little known. Experimental techniques are needed that would allow us to measure the effect of these large strains at crack tips on chemical reactions. It allows us to see what's really happening at a crack tip. And then sort of finally, if we could model, I really believe that will come in the future, if we could model fracture in these materials, when I say robust, that they work fairly well and easily use, not just the people who work in quantum mechanics, that would go a long way to be able to select and predict the behavior of materials for the future. And then I must, at the end, then acknowledge a lot of the people who have worked with me over the years and continue to work with me in this endeavor, and how much I've enjoyed my collaboration with them. Thank you.